Welcome to Hot Chips 27. Session 6. Applications.
This is the application session. I'm Forrest Basket, your host. Our first speaker is one of a long list of co-authors, but is Hiroe Iwasaki. She received a BE and PhD degrees in information science from the University of Tsukaba in Japan in 91 and 96. In 91, she joined the Switching Systems Laboratories at NTT. She's currently a senior researcher in engineering in the NTT Media Intelligence Laboratories. And she's going to talk about professional H265.
Thank you, Chair, for the introduction. I'm Hiroe Iwasaki from NTT. I'd like to talk about a professional H.265 HEVC encoder LSI toward high-quality 4K 8K broadcast infrastructure. Its development code name is NARA, which stands for Next Generation Encoder Architecture for Real-Time HEVC Application. I will start with a bit of background by briefly introduction the history of NTT's video codec LSIs, roadmap toward 4K 8K ultra high definition TV, the latest video coding standard HEVC, and 4K 8K broadcasting requirements. Then I will describe the NARA architecture, including its key features and functions for single chip and multi-chip configurations. After showing NARA chip implementation and target application, I'll conclude with a summary. This figure shows the history of NTT's video codec LSIs. First, we have developed encoder C and M chipset that supported MPEG-2 video coding in 1995, when video processing was changed from analog to digital. After that, we developed a super encoder series for broadcasting. Then we developed a single chip high definition TV MPEG-2 codec LSI. At the time, standard definition TV was being shifted to high definition TV. One of these LSIs was used in practical broadcasting. After that, we developed H.264 codec LSIs. Thus, this LSI was presented at this conference in 2007. Now we have developed NARA, which was supported the latest video coding standard H.265 HEVC. This shows a roadmap toward 4K 8K ultra high definition TV, which was actually announced by the Japanese Ministry of Communications. As we can see, 4K broadcast over satellite began in 2014, and 8K test broadcast will start for big sports events in 2016, and both will be available for commercial TV use in 2020. 8K is not a dream, it's on its way and will be here soon. And now we come to HEVC, the latest video coding standard. It was issued in January 2013, and its range extensions were issued in April 2014. It only has the bit rate of previous standard H.264 and one-fourth that of MPEG-2, which is now used for current digital TVs. High compression is needed for the increasing numbers of ultra-high definition TV video data, so it is a key technology for 4K, 8K broadcasting. This shows the basic common video coding framework. The basic structure of transform and quantization and entropy coding has not been changed for a long time, but intra and inter-prediction improvement is the key to better coding efficiency. Intra-prediction is prediction with a video frame. Encoding beings from the upper left of a picture to the lower right. So you can copy the pixel data from the already encoded upper left region's pixel as a prediction. That's the idea of intra-prediction. On the other hand, inter-prediction is frame-to-frame prediction. When encoding a frame, pixel data are block copied from already encoded frames with a motion vector which represents the motion of objects. Template matching is usually used for motion vector search, finding a place with a minimum sum of absolute differences. With HEVC, a huge combination of prediction tools and modes is needed to perform inter-inter prediction. On the intra side, H.264 has only 8 prediction directions, but HEVC has as many as 33 prediction directions plus DC and planners, so 35 modes in total. Block size variation also increases. On the inter side, H.264 mainly has 4 block size, but HEVC has a hierarchical block split structure. From a coding tree unit of 64 by 64, you can arbitrarily split it into smaller coding units as small as 8 by 8. And coding units can be further split into multiple prediction units with individual motion vectors. As a result of intra and inter prediction as shown in the sample result, various sizes of intra and inter blocks are mixed. As you can see from the huge number of candidates, you must find optimal combination to get a good coding efficiency. This is just a processing time comparison of software encoders. HEVC encoding requires about 30 times as much time as MPEG-2 and about 5 times as much as 8.26 hole. There are the requirements necessary to achieve Hokkei 8K broadcasting. First, it is necessary to prepare a practical Hokkei 8K broadcasting infrastructure in 2020. Second, the latest video coding standard H.265 HEVC has very compression, so it is suitable to build a broadcasting infrastructure for 2020. Color signal robustness against tandem encoding is also needed. It's also necessary to achieve a 600 megabit per second bitrate for Hokkei 8K contribution. To meet these requirements, we have developed a professional H.265 HEVC encoder LSI aiming toward a high-quality Hokkei 8K broadcast infrastructure. NARA architecture has three main concepts. First, the NARA needs several application-specific hardware blocks for processes with high computational complexity, such precise motion estimation. Second, it needs a hierarchical pipeline scheme for decisions on optimal hierarchical coding, prediction, and transform unit size with high compression. And to achieve practical encoding system, we adopt a single chip configuration for Hokkei and a multi-chip configuration for 8K. This is a block diagram of NARA. As I mentioned earlier, with HPC, a huge combination of prediction tool and modes is needed to perform intra and inter-prediction. Therefore, NARA's prediction core consists MED, IPD, and motion estimation. Here, so processing intra-prediction and inter-prediction motion estimation. On the other hand, inter-mode decision, shown as IIM, requires computation flexibility because mode decision parameters need to be updated with picture characteristics. According, the RISC CPU embedded software controls the IIM processing parameters. The prediction part consists of a single core because it can make full use of HVC's strong correlation between neighboring prediction modes. Once prediction modes are determined, the dual coding core performs the remaining functions in parallel for high-speed throughput. A multi-chip connection is also provided and supported with external interfaces. I'll explain this in detail later. Next, I'll turn to pipeline policies. NARA has three pipeline policies. First, it needs parallel processing for precise motion estimation so as to achieve better coding efficiency. Second, for mode decision, strictly sequential calculation is desirable for precise evaluation of coding bit cost. Finally, it is very important for the pipeline stage to be short for efficient rate control. The overview shows the NARA pipeline scheme. A CTU-based hierarchical pipeline scheme is used for high compression. Filter mode decisions are made to achieve coding efficiency while keeping image quality. In MME, parallel pre-decision is performed to squeeze from 4 to 3 sizes. And then IME and FME, 3 FMEs, are performed parallel calculation. This achieves precise motion estimation. In IIM, full tournament mode decision is proceeded. This achieves strictly sequential calculation desirable for mode decision to precisely evaluate of coding bit cost. This slide shows the parallel pre-decision in MME. For motion estimation, the MME performs sum of absolute differences as in parallel for the 8 by 8, 16 by 6, 16 by 16, 32 by 32, and 64 by 64, sum of absolute differences blocks, and then parallel pre-decision squeeze from into 3 block sizes. Here we see block size parallel motion search in the FME. Motion estimation is performed in parallel with computationally complex processes. In the search process, motion estimation is performed for 3 block sizes. Since there are several pipeline stages, this ensures that an enormous amount of calculation will be performed so that better coding efficiency can be achieved. In IIM, modes are decided by strictly sequential calculations through full tournament mode decision. This is very important as a means to precisely evaluate coding bit cost. This shows NARA configurations. In terms of capability, the single chip process achieves up to 4K 60 frames per second for 2. The multi-chip scalability process achieves up to 8K 60 frames per second. In order to process the 8K 60p, 4 LSI are required. This slide shows multi-chip configuration in more detail. When encoding one picture in multiple chips, we need to have a mechanism that will not lower the compression efficiency. The reference image and deblocking filter and sample adaptive offset image near slice boundaries transfer to the neighboring chip. This is very important as a means for keeping the image quality. NARA has a number of key features and functions. For a single chip configuration, complicated HEVC processing is mapped to a hierarchical pipeline scheme based on coding tree units. The hierarchical pipeline achieves wide-range motion estimation and optimized HEVC's high-precision prediction mode decision. NARA also achieves 4K 60 frames per second 422 real-time encoding with ultra-low delay for field pickup units, high bit rate of up to 600 megabit per second, multi-channel encoding for cloud systems, and multi-standard encoding for allowing smoothing migration. For a multi-chip configuration, Nara encodes ultra-high definition TV beyond 4K with motion estimation and loop filtering across split boundaries when each chip encodes a partitioned frame. And it is suitable for HEVC-based tandem encoding with HO22 for keeping good color information and two-pass encoding for higher compression of final distribution. Here is a NARA LSI. For precise motion search, the LSI has a large reference picture image cache and 3 DDR channels. There are several risks in order to adjust video image quality by embedded software. This PCI Express interface is for transferring data to the neighboring chip. There are NARA's physical features. The LSI was fabricated by 28 nanometer CMOS and the number of transistors 83 MHz. The clock frequency is maximum 600 MHz. It's lower than 600 MHz when encoding performance is under 4K. The supply voltage is here. So the power consumption is typically 15 watts. The package size is 35 millimeters square. And these are its functional features. The video profiles are H.265 and H.264. Its motion search range is very wide. The LSI supports 4K by 2K at up to 60 frames per second for single chip, and 8K by 4K at up to 60 frames per second for multi-chip. The LSI also supports other interfaces. Here we see target application samples such as digital TV broadcasting network service. Both contribution and distribution transmission are needed in the broadcasting infrastructure system. Programs are made by contribution transmission, and very high quality is required. In making the programs, several encoding and decoding processes needed to be performed until the very end. If encoding decoding is done 3 times, the 420 image has damage. There is a little bit differences, but it is very important for contribution system. So the contribution quality needs HO22 color formats. Since NARA supports HO22 format, we can propose it be used in both distribution and contribution system. Other target applications for 4K, 8K HEVC are shown here. There are not in the area of broadcasting, but also include applications in cinema, medical, industrial design, and so on. High resolution will open the door to many more applications in the future. Conclusion. In summary, then we have developed a single chip 4K 60 frames per second HO22 HEVC video encoder LSI we call NARA. It's suitable to 8K 60 frames per second, and this scalability is achieved with inter-chip connectivity and parallel processing function. The NARA architecture has a hierarchical pipeline scheme for CTUs. NARA is a key LSI for professional H.265 HEVC encoder LSI dual high-quality 4K 8K broadcast infrastructure. Thank you for your attention.
So we have time for a couple of questions. I see we have one queued up over here. Would you like to start?
My name is Tadao Nakamura, Kurchips Conference Series. Okay, you are planning on introducing your technology into the Japanese 8K TV projects for the 2020 Tokyo Olympic Games, is it right?
Yes.
Okay.
We have planned, so broadcasting system will this chip.
Okay. Presumably, I understand. Okay, next question. Could you show me the details of memory systems of your chip?
We have a big memory in this chip, so about 200 megabits, and the LSI connected to 3 DDR3 channel for wide motion estimation.
Okay. Thank you very much.
Okay, Bob?
Bob Stewart, Stewart Research. Could you describe the transform and the inverse transform that you were using?
Transform algorithm, and now the algorithm for transformation, so for H.65 according to H.265 standard.
What do they do?
Sorry, this LSI has not so special algorithm. Only according to H.265 video coding standard.
I think she's saying they use the standards according to 265, Bob.
Okay, but it'd be nice to know what they did.
Why don't we thank Hiroe? So our next speaker is from Anitoa Systems. It's Zhimin Ding, and he's going to tell us about ultra-low light CMOS biosensors that help tackle infectious diseases. Zhimin is the founder and CEO of Anitoa Systems, a company that has offices both in Silicon Valley and China. He was previously the chief architect at SST, a company that was later acquired by Microchip. And prior to that, he worked for Philips Semiconductors. He earned a PhD in electrical engineering and neurosciences from the University of Illinois at Urbana-Champaign, and a bachelor's in EE from Tsinghua University in China. Zhimin?
Thank you, Forrest. Good afternoon. It's a great pleasure of mine to introduce to you some of the work we have done at Anitoa Systems. in the space of CMOS biosensors and also the application of such sensors in fighting infectious disease. As we know, for most part of human history, infectious disease has been a #1 killer of humankind. Now, even in today's technology, infectious diseases still manage to kill about 16 to 17 million people each year and affect the life of many more. In fact, in the last 10, 20 years, we have seen a resurgence of drug-resistant infectious pathogens in all kinds of different settings, including hospital settings, and that really have worried healthcare professionals. So the Ebola outbreak last year in West Africa has also underscored the importance of having a globally affordable tool to help fight infectious disease. And one of such tools that's we think is very important that we're going to be talking about is a precise and rapid diagnostic technology that will give doctors the necessary information to prescribe effective drugs that not only help the patient but also prevents the further spread of infectious diseases to the larger population. Well, one of the most exciting developments in this area, also roughly in the last 10, 20 years, is in a technology called molecular diagnostics. This is the technology where diagnosis is focused on understanding the molecular, in this case, mostly DNA, RNA contents of the pathogen. And one of the key benefits of this technology is very specific. So for a given disease or symptom, it will give doctors precise information about the type of pathogen, how they react to the drug. But the problem is this technology today is still not widely available or definitely not in a timely fashion to a lot of people around the world. One of the reasons is because the equipment is so bulky and expensive and the process to operate those equipment are so tedious that they have to be confined in a professional lab space and operated by specially trained operators. So today, if someone needs to get diagnosed with some kind of infectious condition or sometimes cancer, the sample has to be taken from the patient at the hospital and then transported to the lab. So the turnaround time can be days or weeks. What we are trying to propose or envision is a technology will allow diagnose at that kind of accuracy on site with a much more portable device, and that's much easier to operate. And that also provides what we call actionable information to the doctors. So when we say actionable diagnostic information, it's something that's more than just a yes or no answer. It usually will tell the doctor whether it's a drug, is a bacterial or viral infection, whether it's a drug-resistant type, or in some cases we need to quantify the pathogens, so doctors can make intelligent decisions about what to do next. So what we are envisioning and we are actually putting together is something that will give doctors that level of information in half hour to a couple of hours. So a little bit step back on what has been developed in the last few years, and also people, many of you may have read about this type of story, is that people have been innovating in an area called microfluidics. So this is a chip that can house reactions between patient samples and assay reagents in a very compact platform. But what people usually do not tell you when they show their work with microfluidics is what's behind. So here we're showing a system from Beckman Coulter, and this is a system called AmpliGrid system, where they have a little handheld compact chip that can run a lot of reactions that give doctor a lot of information. But what they usually don't show is in the background, you need to have such a huge machine that read out this chip. And also we have incubators and robotics that move the chip from the incubator to the fluorescent microscope where they can perform the readout. So the whole system is definitely not compact enough for point-of-care diagnostics. So that's why we think the instrument needs to be small too. So the key to make an instrument small is the biosensor. So let me give you a little idea about the landscape of biosensors. So today, I'm going to focus on two types of biosensor. One is an electrochemical sensor, and the other is an optical biosensor. So on the electrochemical sensor side, the most famous, everybody knows about the success in electrochemical biosensor is glucose sensors that diabetic patients use to monitor their condition. And then on the optical side, most of the molecular diagnostic equipment today use some sort of optical sensor. And the sensor usually is either a PMT or a CCD, or in many cases, cooled CCD to reduce noise. A PMT, let me just point out, is actually a vacuum tube. So it's kind of ironic that in this conference, when people are talking about 100 billion transistor CMOS chips, we're still talking about how to replace a vacuum tube. So those sensors, they have very, very low level of noise, so they can sense very low level of light, and that's essential for use as a biosensor in a molecular diagnostic application. So wouldn't it be nice if we can replace that with something that's more familiar to us, a CMOS chip that's highly integrated and that's very low cost, yet it has that kind of sensitivity. So that's what we are doing today, and I would like to introduce that to you. So this is just basically what I've been talking about in the last slide, that there's a landscape of different type of sensors, either electrochemical or optical. On the optical side, the reason that we need ultra-low light sensitivity is because the probes that we use in diagnostic assays, they usually emit very low level of light or change of light when they interact with the target's analyte, which could be DNA or RNA from pathogens. Also, those signals are very narrow band. So in order to have the best signal-to-noise ratio, so we want to use filters also to restrict the sensing spectrum to a very narrow band. So that means the amount of energy that arrives on the pixel is very, very small. Now, on the electrochemical sensors, let me just add a point that even though it has been very successful in blood glucose testing, but its success hasn't been extended much far beyond that because they suffer mostly of this specificity problem. So obviously, when you are looking for a particular pathogen, it's immersed in a much larger population of other cells or molecules that we are not interested. So you don't want the sensor to react to those other things that you're not interested. So specificity is as important, if not more, than sensitivity. Lastly, there are sensor technology which are integrated into the assay. So in other words, they come in close contact with the sample. And this type of sensors obviously will have better sensitivity, being optical or electrochemical, but they carry a cost implication. So with that, I would like to introduce to you a CMOS ultra-low light biosensor that we have developed at Anitoa Systems. So this sensor can provide a detection threshold as low as 1 millionth of a lux. Or actually, I'm showing 3 here because we are talking about 3-second integration time. But with longer integration time, we can work down to 1 millionth or even less light. So what does this mean? So today we have scientific CMOS sensors that can be used in scientific or military applications that can sense light level that's like 1,000th of a lux. And 1,000th of lux is as low as in a pitch dark, low moonlight, low star kind of environment they can sense. But what we are doing here is 1 millionth of a lux. So it's another 1,000-fold improvement over today's scientific CMOS sensors. And so this sensor can get that kind of a low detection threshold with a good signal-to-noise ratio, and it gives a wide dynamic range. And this is a highly integrated sensor. So it has A to D converters integrated and very low power, so that the signal that comes out of the sensor is digital serial signals. We are using a fairly large pixel in this sensor for two reasons. Obviously, big pixel has a better light collect efficiency, but also big pixels allow us to do other things on the pixel directly. So a little bit description about the type of innovation that we put into the sensor to make it low light sensitive. It turns out that there are several areas that we can innovate. They range from a process innovation to analog and to digital. Turns out that we have to do all of them to achieve the type of sensitivity that we want. So on the process side, we work with our foundry partners to create a special pixel that has very high responsivity and very low dark currents. And then on the analog side, we carefully analyze the type of noise that comes out of the sensor because of the limitation of the physics. So there are short noise, which is more temporal random noise that's inherent in a solid state device. And then there are reset noise, and then there are fixed pattern noise. So we use divide and conquer approach to separate those noises and then suppress them as much as we can. And in the end, we use advanced DSP algorithm to further extract the signal among the noise and achieve a good signal to noise ratio. And this is just a diagram of how multiple sensors can be integrated into a embedded system, and they can be done in a very simple manner with a serial bus that can have multiple sensors hanging on the same bus. So we did some characterization of this sensor, and the first I would like to explain is a characterization of sensor in the context of detect double-strand DNA in a non-specific fashion. So we use an assay that we sourced from Life Technologies. And this is an assay that will bind with double-strand DNA and generate fluorescence signals in a proportional manner. And with our sensor, we are able to achieve pretty good linearity and detection thresholds, 5x better than the method that's being used, 500 times better than the method that's being used today, which use absorbance type of detection. But this is not quite diagnostics yet. This is just to quantize DNA, but it doesn't really recognize the DNA sequence. So as I mentioned before, that microfluidics is an important innovation in miniaturization of diagnostics and a lot of other biochemistry. So when we design our sensor, we keep that in mind, and we try to combine our sensor with microfluidics to come up with a system solution for molecular diagnostics. So here we're showing a microfluidic chip where the reaction takes place between a patient sample and our diagnostic assay, and a imaging system that employs multiple of the biosensors that we have with filters and lenses as a combined solution. And with this solution, we have put together a handheld format device that can be used for infectious disease diagnostics. And the advantage of this device is that it's very small, it's easy to carry around, and there's no moving parts inside the box, so everything's fixed and solid, so it's very reliable. And it has extremely high sensitivity and high degree of reproducibility. And I will explain a bit later with some data and applications. So also I will explain later why low cost is important. So this is a device that we put together with CMOS sensors and no moving parts, no high voltage power supply, no highly complicated A to D boards. So it's everything is digital and everything is consumer type of technology. So it can be done very cheaply. And this is just a picture showing what's inside such a device. So as we can see that we have test tubes or microfluidic cartridges where the reaction takes place, and then we need to thermally manage the assay so that we can control the reaction. And then on the readout side, we have optical excitation using LEDs and filters to excite the sample, and then we use our sensor to sense the emission of fluorescence or chemiluminescence signals from the interaction between the probe and the sample. One thing I would like to also point out is using microfluidic cartridge instead of standard tubes has the advantage of being able to integrate other upstream process. So one of the importance of diagnostics is to be able to achieve sample to result, meaning that if you take a raw patient sample, let's say blood or a nasal swab, you can extract DNA and detect DNA at the same time so that you can minimize hands-on time. So that's one of the key advantages that's provided by microfluidics. And here's some results. So we are running a reaction that's called a polymerase chain reaction. It's a quantitative real-time polymerase chain reaction. So in this kind of reaction, the patient samples that with DNA extracted would would go through a process where they can replicate itself many times. And during that process, they would bind with a specially designed probe molecules that will specifically detect a certain sequence in the DNA or RNA. And the enzyme that we use to facilitate this kind of reaction is controlled by temperature, its activity. So we use a temperature cycle to cycle through the to cycle through the sample. And as we do that, then the fluorescence output goes through this kind of change as a way to tell whether the reaction is taking place or not, whether the particular strand of DNA that we're looking for is present and therefore reacting with the probe or not. As we can know that here, the baseline is a negative control. So without any target DNA we're looking for, the output is pretty flat. And then with the target DNA at different concentration, we see different type of curves. So we can use this to not only detect yes or no, but also quantify the target analyte. So the previous example that I'm showing here, we used a bacteria DNA called E. coli. This is kind of a gastrointestinal bacteria that we use. And then in the next one, we're also applying this to hepatitis B. It's a, hepatitis, as we know, there's a large population around the world that has this condition. And hepatitis B is known to cause cirrhosis or liver cancer in a late stage. And there are many drug-resistant variants of hepatitis B. And then the drug that's effective for those variants are different. So this table basically shows how different variants are, how drugs are sensitive to different variants. So it's essential for diagnostic to be able to detect not only yes or no, but also those mutations. And in addition, of course, as patients start to take medicine, we need to monitor the virus counts within a given volume of sample. So quantification is also important. So we developed all those technologies so that we can give information to the doctor that doctor can use to decide on the treatment. So one of the advantages, of course, is doctors do not have to use what's called a shotgun approach, which a lot of doctors are using today, where they just give you a lot of drug and see, one of them will work, but then there's going to be more side effects and also more reasons to cause further drug resistance. So this is the approach that we're trying to avoid by having this kind of precise diagnostic information. So there are some other applications that we're working on, and that's very promising. And I would like to give you a explanation of why those applications. So definitely the first class of application that we're mostly interested on and we are pursuing is a upper tract infections, upper respiratory tract infections, basically flu. As we know that this is a seasonal disease that can affect as many as 30% of the population when there's an outbreak. And one characteristic of this type of disease is from symptom to treatment, the window is very short. So when people is infected, they need treatment typically within 24 hours if it's a viral type of flu, like influenza or H1N1, H7N9. And also this is very contagious, so people can transmit disease to the next person if they are not being helped. So therefore, time is essential, and then with a on-site kind of quick turnaround diagnostic, it really can help. A second kind of class of disease is what we call hospital-acquired infections. So a lot of those kind of bacterial diseases are harmless in a healthy people, and as a lot of doctors and nurses they actually carry those kind of bacteria because they get exposed to them so much. But when patient is in a surgery or in a cancer treatment, then they need to suppress so to avoid complications such as sepsis or pneumonia. And so this is very critical, and a lot of those are now shown to be drug resistant. So we need to have a way to control that, and it needs to be really quick. So lastly, I would like to point out that our solution, as we know, by using a CMOS biosensor instead of very exotic sensors like photon multipliers or cooled CCD, is that it's low cost. And it's very important. Why? Because if we want to compete with the central labs, we need to be very low cost because they reduce their costs by running large batch of tests in a kind of a pipeline of method, so the per test cost is very low. So we have to match that in order to be successful, to compete with that, in addition to being much quicker. So this is basically what we're trying to say, that we're trying to democratize molecular diagnostics. So there are some other applications for the ultra low light CMOS biosensor, and I would like to just pick a few. One of the first application is it's very different from what we're doing. So this is an application where you use fluorescent imaging as a way to guide surgery, especially cancer or tumor surgery. So one of our customers is using our chip in an endoscope that can image the cancer cells. So basically, you can use a fluorescent labeled probe, some kind of antibody, give it to the patients, and then when that probe is being applied, then the cancer or tumor tissues will just light up with a very weak level of fluorescence. And with this kind of special endoscope, then doctors can see visually what's the contour or shape of the tissue that needs to be cut. The other is cell sorting. So this is an application where you can quickly image the cells to see if it's a cancer or not. And this is very important because today people are doing, find cancer cells in blood instead of using biopsy, and then it can be much more accurate and much less painful. And this is just a show of some of the development we have done, and we taped out the chip a couple of years ago, in fact. And then we spent a long time doing a lot of testing and validation, and now we have created a development board where we have sold to many partners who are doing many kinds of different applications using this chip. And then we plan to commercially release this chip and associated development system towards the end of this year. So to summarize, a ultra low light CMOS biosensor can make a huge difference in how medical diagnostics are being performed today, and we want to develop along that line to create smaller and much more compact, yet very sensitive and very specific test platforms for all kinds of infectious conditions, as well as cancer that we are looking at. And then we are also looking at a very high-speed version of this chip to help with cell sorting. So in also as a part of the effort to fight cancer. So this is just my story, and yeah, if there are any questions, I will be very happy to address.
So we have time for a few questions, if there are some out there. Let's see. Here we are. On this side first, you were here first, right?
Okay.
Hi, Koji Suginuma with Visual Communication Journal. So it is a great sensor, and I'm expecting your sensor is being installed in the product soon. And my question is about the sensitivity. So the CMOS sensor has a very wide open angle, like 150 micrometer, but it doesn't explain the reason of the high sensitivity. What is the secret?
Yeah, really, I think the most important technology underlying reduction of noise is to really understand from very precisely the type of noise that may be present and try to separate them, and then using different type of techniques to reduce. Like, for example, a reset noise is very different from shot noise and also from fixed pattern noise. So we have different algorithms to deal with that. And some of them are better done at analog level, like reset noise. Whereas shot noise, obviously, you cannot really reduce them. You can only average them. So that's done in the digital. But also we are trying to reduce the dark current so that as you use very long integration time to essentially give you more sensitivity, the dark currents do not saturates your output and then reduce your dynamic range. So really divide and conquer, that's basically the approach.
So do you use the plain vanilla CMOS process or some special process?
Well, it's a CIS process. So it's a special image sensor process, but it's from a commercial foundry. So
Thank you.
yeah, right.
On this side?
Joshua Wise, NVIDIA. I was wondering, you mentioned that you have a 12-bit ADC and also that you achieve 85 dB of dynamic range. And I was wondering how those two line up. I was wondering if you do multiple exposures to get extended dynamic range.
Right, yeah. In fact, the sensor has two operating modes, a low gain mode, a high gain mode. So they operate together. So it can actually extend to effective resolution to about 15 bits.
Okay.
Right. So we are doing actually two captures and then.
And you merge them on chip or off chip?
In digital domain.
Okay, thanks.
Yeah, thanks.
And another one over here.
Nathan Brookwood, Insight 64. Since you're operating in the domain of healthcare, I'm wondering what impact, if any, the FDA has on your activities. Do you need any special approval in order to get your products into the market, or how does that work?
Yeah, so one of the first application is what we call near patient diagnostics. So it's still in a hospital setting. So it is subject to the same FDA approval procedure. Especially we plan actually to bundle the instrument with assay, with the chemistry. So it's kind of a type 3 type of approval procedure. And then we are also exploring using this in a more kind of consumer space as a home diagnostic kits for like flu, right? Like a kid gets a flu, and the parents may want to use that to get some idea about what type it is. So that's where we are still exploring. In fact, we are working in China right now, where they are a little bit more flexible to find a way to put that in the home.
So do they have to bless what you're doing in any way, or is your activity directly with the hospital?
Yeah, so for home use, yeah, they have their version of FDA. They have some kind of regulation on what kind of accuracy you can, but then you also have to make sure that it's more advisory type of information. It's not a diagnostic information.
So right now you don't really have to deal with them.
Yeah,
or the hospital.
Yeah, so our focus is currently is hospital, but we are working on a home version of this device.
Thank you.
Yeah, it's an ongoing process. Yeah.
Okay, I think that's it. Let's thank their speaker again.
Thank you.
Great, thanks. So our last talk is by Ramin Shirani and Ramin Farjad Rod from Aquantia. And the talk is about 5 different speeds of Ethernet over legacy copper. Our first of the 2 pair of speakers, Ramin has been the co-founder and senior VP of engineering at Aquantia and has done all the things that you might think that a senior VP of engineering and co-founder has done, which is a lot. In addition, he's been granted 21 patents and has 10 pending patents in the area of IC design and communications. His co-author, the other Ramin, is a leading architect of high-performance communication systems. He's the company chief architect and VP of technology, and he's had over 70 granted and pending U.S. patents as well as publications. So we'll start with Ramin.
Thank you very much, Forrest. So let me start by telling you that today I'll be talking about a 5-speed physical layer Ethernet chip going from 100 meg to 10 gig. 100 meg really dates back to 1993, 10 gig 2005. The innovation really that I'm going to talk to you about would be the 2.5 gig, 5 gig. So let's look at the mega trends driving the need for next generation Ethernet connectivity. One of the things that we all have in common, almost, I would guarantee almost all of us, right, other than the fact that we're all engineers, or most of us are engineers, right, is that we carry a cell phone, right? That's very true. You all agree with me, right? So what do we do with the cell phone, right? We access data, we access email, social networking, Facebook, eBay, you name it, right? There's a lot of push to put the data in the cloud. And what we want to do is be able to access it with our, cell phone, our friendly cell phone. Effectively using this, right, this ecosystem of the insatiable thirst for bandwidth to the cloud back to our cell phone creates a bandwidth constraint on the IT, infrastructure. And what we did a few years ago is we said we're going to go focus to solve a piece of the puzzle, which would be the connection between this wireless access switches to the AP devices, to access point devices. And if you look at this chart, right, effectively what you see is that there are about 2.5 exabytes of data in 2014 based on Cisco. And honestly, I didn't know what exabyte is. I had to Google it myself a few months ago, right? But it's 10 to the 18 bytes of data per month. And it's going tenfold to 24.3 exabytes in a matter of 5 years. So the insatiable thirst for data growth is obviously very, is inevitable. Let me start by talking to you about the enterprise network structure. And you can see this in the white papers from Cisco and various switch vendors. The 3-tier design approach, and I want to kind of zoom into where we come into the picture and what piece of the puzzle we solve. Effectively, at the core, you have the core switches, the likes of Nexus platform switches from Cisco. Distribution would be the 4500 class switches, the Catalyst switches from Cisco. And I'm giving you an example of Cisco because I'm fairly familiar with them. And then the access would be the lower-end Catalyst 3750-like devices. And the connectivity between these access point switches to the AP or to the desktop is where we focused, right? This connection right here, and I'll show you in the next few slides, are primarily today in the enterprise environment are being driven on Cat5e and Cat6, right? More than 70% of the enterprise campus wiring, right, is either Cat5e or Cat6. To go replace them is a very costly proposition. To go put another one is a costly proposition. You're looking at $300 to $500 per cable run, which makes it really prohibitive for existing infrastructure. So back 3 years ago, we said, hey, what can we do with the upcoming migration of wireless access to 802.11ac, he said we should kind of resolve this bottleneck, create a technology that can run on Cat5e. So this really puts it in perspective, right? You would see that the progression of the wireless access standards from 2 megabit, maybe a decade ago, now to 802.11n, which is commonplace, and the wave 1 and wave 2 of 802.11ac as part of the upcoming deployable access points requires multi-gigabit of data throughput. If you have a wireless access point and your bottleneck becomes this 1 gig, 1 G base T here to the switch, what's the use of having 802.11ac wireless access, right? It really becomes, in a way, useless. Unless the data is, through one user here back to the user, the data really needs to traverse and go to the switches. So if you look at the legacy infrastructure and what's installed today, majority of these links are 1 G base T, and the cabling is, for the most part, Cat5e and Cat6. I've shown a picture of it here. And what we set out to do, we said, we want to go solve this piece of the puzzle, be able to run multi-gigabit, effectively 2.5, 5 gig on this legacy cable, and therefore the work toward this product. We formed the N-Base-T Alliance as a founding member with over now 40 participants, and we're very actively, myself and a few of our other people are actively involved in pushing this into the standard. And for now, it's been accepted as the baseline in the standard. So the multi-gigabit application space. The only reason I'm showing you this, right? I remember I had an instructor back at 1989, UC Santa Cruz Extension. I was taking classes for Ethernet. His name was Rich Seifert. Some of you may remember him, right? One of the things that he taught me many years ago was when you create a fat pipe, when you create a faster pipe, right? Don't worry so much about killer applications of what's going to come and fill it. Once you have the pipe, the killer applications will come. And that's exactly what we're seeing, right? If you look at this picture, we set out to really solve the connectivity between the wireless access and the switch. Now we see a fairly important uptick in the demand for the client side, where low-end servers and high-end workstations want to connect to the switches. In the enterprise, effectively at 2.5 gig and 5 gig, a very interesting applications which just spawned, and we're looking at it very carefully and working with key suppliers, is what they call CRAN, right? The Cloud Radio Access Network, where the cell phone data is digitized and run on 200 meters of copper cable to a central location. For those of you who are interested in that, you can look at the AQ cell in Aquantia website. But what I'm trying to say is that once you have a fat pipe, many applications will come about where we didn't even perceive of it 3 years ago. So what is the signaling? Let me just spend a few minutes quickly without boring you with the detail of the specification. From 1000 base T back in late 1999, 2000 to now in 10G base T in 2005, 2.5 and 5 gig in the past, basically a year. The mechanism of transport of data has been to run dual duplex on 4 pairs of twisted pair cable, right? There's a significant challenge in doing dual duplex. Dual duplex means that you receive and transmit on the same wire, right? So effectively, you have to cancel your own echo. And this is very non-trivial. If you imagine running on the same wire, you have to cancel your own near-end crosstalk from the adjacent cables. You have to cancel far-end crosstalk. You have to allocate enough signal-to-noise ratio for a 6-around-1 configuration where the victim in the middle is being bombarded by radiation from the adjacent lines. And you have to also take into account environmental specific interferences. And an example of an environmental specific interference would be impulse noise, right? This is something we learned by studying the enterprise environment very carefully and understanding the issues involved in enterprise. One of the key factors which is different, and I'll show you a picture of enterprise versus data center. 10G-based being a data center play, whereas what 2.5, 5 gig is really an enterprise play. You see that there's very, electrostatic discharge events are fairly common in enterprise. Effectively, what are these events, right? In enterprise, you got furnitures, you got chairs, you got many different medias, and in fact, what we noticed was when you sit on a specific chair or touch a specific chair, the electrostatic discharge of what you generate, the mechanical distress of the furniture would cause an electrostatic discharge, and we've captured it here visually. And effectively, this would be narrow enough that in frequency domain, it would distort your incoming data by common mode coupling into the cable becoming differential, and then you get errors. So ESD and the consequences of ESD was very fundamental for us, the way we decided to architect 2.5 gig, 5 gig, as contrast with what we had in 10G-based D. So a picture is worth 1,000 words. You see that data center, you really have neat wiring, very well managed, very controlled environment. And unfortunately, many data centers, they've kind of grew over time. They just put more and more cable. The frequency of interest was 62 megahertz because of the limitations of the bandwidth of 1,000 base T. And there's poor cable return loss, really leading to large impulse reflections and in full duplex link. So effectively, what I'm telling you is to take a solution that was for data center and try to adopt it readily as is for enterprise would have been a disaster because it wouldn't have worked. So another factor, right, without, again, going into too much of the technical detail here, but another factor is you have a transmitter, you have a receiver, and effectively your transmitter has finite linearity, right, from a spectrum perspective. And in a data center environment, it's clean, but in an enterprise environment as such, you would have a lot of imperfections and non-idealities. You would have reflections of magnetics, of the RJ45, of improper terminations, and any non-linearity from your transmitter reflecting back, right? Let's say at 250 megahertz, at 190 megahertz reflecting back is uncancelable with the traditional DSP linear processing. You really need nonlinear cancellation, and it would become cost prohibitive. So this was another key consideration for designing something for enterprise. So let me spend a minute. I'm not going to bore you with the detail of signal processing here, but effectively 10G-based back in 2005 adopted 128 DSQ, right? What does this mean, right? This means that effectively you don't put zeros and ones on the cable. What you put on the cable is you put multi-level encoding, right? 100 meg Ethernet was 3 level, 1000 base T was 5 level, 10G base T is 16 levels, but it's done in 2 dimensions, where in one point in time you put one PAM16, which is 16 levels. In the next 1.25 nanosecond, you put another effectively PAM16. You deprune it to create more Euclidean distance for more resiliency. And effectively, that's what, what the constellation and the coding is for 10G base T. The shortcoming of this and kind of relevance back to what I showed you on impulse noise and on the linearity issues is that your least significant bits, of 4 here, right, in this coset, are entirely protected in 10G base T with a forward error correction. So effectively, if you get an impulse noise, right, and the noise comes in, couples onto the cable and into your system, you will correct the errors in the least significant bits. In the most significant bits, however, you're only protected by the Euclidean distance. Effectively, the Euclidean distance is the distance, let's say, from here to here between the various cosets. And a single impulse noise, imagine this, right? A single impulse noise coming in goes in, couples into the cable, causes the most significant bit errors, and effectively, as a consequence, you lose a whole packet, right? Could be 64 byte, could be 1518, and then your TCP/IP have to react and renact, and it's chaotic. So you really don't want to carry any uncoded bits. So what we decided to do is we said, okay, how do we protect all the transmit bits in LDPC? We decided to use gray-coded PAM16, PAM16 is basically pulse amplitude modulation, 16 levels, and it's 4 bits per symbol. 2 adjacent symbols gives you 8 bits. And what we did was we freed up enough bits, effectively losing a little bit of Euclidean distance. We freed enough bits to encode all the bits involved in making this chip work. The combination of LSB and MSB bits combined in LDPC or coexisting in LDPC also give us an additional 1 dB gain. And to make a long story short, what I'm telling you is that the robust non-stationary impulse noise and analog front-end imperfections are taken care of with this sort of a coding, right? This is fundamental. If we would have just taken 10G base T and scale it down, right, from 800 megahertz to 400 to 200, so on and so forth, it would have had fundamental issues from working in the field. So I know you want to dive into looking at the chips. After all, this is a hot chips, right? And my colleague, Dr. Farjad, will cover the chip detail with you, and you can ask questions. But from a data flow perspective and physical coding sublayer, the data comes from the media access controller, or the upper layer, the OSI stack layer 2. It's in the form of 64 bits. We encode it into 64B, 65B, scramble it, really to get rid of any kind of a DC imbalance and to make sure from an EMC compliance you don't have any specific data-dependent peaks from when you transmit it on the wire. You LDPC encode it, you PAM16 encode it, and then you put it on the wire. So effectively, this is what's built into the chip that Dr. Farjad will present to you. Thank you.
Thank you. Good afternoon, everyone. So the next slide, I'm going to touch over the top-level architecture and the block diagram of the PHY. One of the issues that, from the early generation of Ethernet we had, starting with 10 meg, going to 100 meg, and 1G, every time the architecture, the DSP coding, everything completely changed. So that meant that the actual design for the new generation of the PHY had to change completely. That was okay in the past because the overhead, the design overall for the PHY was not that significant. Going to 10G, where the actual complexity of the PHY was about 30 to sometimes even 50x larger than 1G, that would have been a big issue if, again, generating 5G and 2.5G, whose in terms of complexity was very close to 10G, and it's mainly because they are also running very close to the Shannon capacity of the channel. If you wanted to pick a different architecture, again for that, that would have been a big overhead for a PHY that wanted to support multi-speeds. That's why what we tried to do when we came up with the architecture of 2.5G and 5G was to make it pretty much the same architecture as 10G, although the modulation and coding and so forth was different. But most of the machinery that we used was pretty much the same, which all we changed was the modulation on the transmit side to add the PAM16 to it, and also on the receive side, kind of like the slicer that is not shown here, small block, and the framer for the LDPC decoder. So everything else is effectively the same. And of course, the power will scale almost proportional to the speed. On the digital side is obvious because you just reduce the clock speed and the switching power will drop. What remains is the leakage power that kind of roughly could stay the same depending how you turn off the headers. And on the analog side, as you go down the speed, you get more SNR and you would be mostly dominated by the alien crosstalk of the channel. We designed it intelligently to effectively reduce the power to kind of match the required SNR in the analog portion. And that's how we managed it. And also on the system side, mainly because at these speeds, especially between 2.5 and 5G, depending on the quality of the network, the data rate could change. We didn't want to change the speed on the system side. That could create a lot of complexity. And that's why there was this new standard, or we call it MSA, US XGMI that also developed by Cisco that always keep the system side to run at 10G, and we effectively send 2 bits, same bits at the same time, or 4 bits at the same time to get effective 5G or 2.5G speeds. So as far as the top level block diagram of the chip that you can see here, on the top part, the green part on the analog, we have 5 receivers, 4 transmitter. The 5th receiver is effectively to measure the alien crosstalk on the chip or on the channel that we receive. It senses that and uses it to cancel it as it converts from common mode to differential on all channels. And that's how we can manage radio frequency interference that will come from your cell phone or from different sources and cancel it and not be affected as much by that. And of course, to manage the different speeds, wide range of speed, we use LC for 10G, which is like a requirement, requires very high jitter quality, down to lower speed goes to like ring oscillators and so forth. We use the same LDPC, and of course, while we get about 8 dB LDPC gain or coding gain for 128 DSQ, that becomes over 9 dB because of the grade-coded PAM16 that we use there. The FIRs, the cancelers that we have for the system for echo and next cancellation and fixed cancellation are here as far as or linear cancelers. And the features that we support are like precision time protocol, energy efficient internet, which is very important to manage the power management of the system. When the links are not always running, you can completely shut down or almost bring it down to like 90% off, and also max security. The chip area is 40 millimeter, and the power for different speeds are 1, 2, and 3 watts for 2.5, 5, and 10G. So as far as the performance and how it performs in the actual enterprise, when we introduced this technology to IEEE, we knew that we were going to go to deploy it for all the types of existing enterprise, legacy enterprise. But at the same time, the issue was all these enterprise networks that have been built from like 15 years ago was designed for 1G, and none of them necessarily, not all of them, followed the TIA requirement specs for alien crosstalk, the configuration that needs to be done, because 1G was, they had enough margin and so forth. And of course, we designed the 2.5G to be as close to 1G, but the problem was we could never be exactly as 1G. And we also knew that some of these networks, they just, as long as they could run 1G on it, they were happy enough, so there wasn't much margin left. So as part of the IEEE effort, we ensured that 2.5G always run on Cat5e, existing installations from a long time ago, with all the alien crosstalk, with bundles and so forth, but with a defined configuration and in a certain use cases. And for 5G, of course, we defined it for mainly Cat6, which is the next generation that the enterprises are upgrading to. As you see, as part of this effort, we defined the alien crosstalk limits, which for 2.5G, we defined it to be 18 dB higher, in a sense, more crosstalk tolerance compared to 10G, both for far-end crosstalk and near-end crosstalk. As roughly, you can say, is about 10x more alien crosstalk that you can tolerate on these links and it still operate. And for 5G, the limit that we defined was 12 dB. Those are the requirements for the system to be able, or cable infrastructure to be able to run these speeds. So to test this, we did it in a different schemes. First was single cable to test the performance of the link, of the PHY performance over just the link by itself without any interference. At 2.5G, we could go almost 200 meters, and that's 18 dB more loss of just the traditional Cat5e. And for 5G, we could go 125 meters on Cat5e and 135 on Cat6. That's far exceeds even what 1G link can do right now. And of course, in a real scenario, when we have the cables bonded together and so forth, we used the cable racks of different lengths that we had to test this. And in these cable racks, the whole length of the cable are bundled. And what we have for a Cat5e, when the whole thing is bundled, we could go as far as 135 meter in cable length. And that's pretty much even more than 5 dB more loss with all the crosstalk that we get from like a basically low quality cable. For 5G, when we added used Cat6, we could go close to 100, almost 100 meter, I should say. And when the full length is 6-on-1 bundled. But the question is, what's the real scenario that we have to deal with? Because as you can see, when we measure the alien crosstalk for this last Cat6 cable that we ran the 5G over, you see it violates the actual bond that we had in certain points, both for far end and near end. Far end and the high frequency, near end and low frequency. Comparing it with what a Cat6A that people run 10G on it, you see we still have a lot of margin compared to the 10G limit, which is much higher than the 5G limit. So, and the question is, will all the 100-meter cables be like that, and would that be a problem? But in reality, when you look at an actual enterprise network, is that not all 100-meter are bundled. You start from the server room, the cables go up to the riser, and then they get split to different wireless access point, different offices, and so forth. And usually, in worst case, the last 20 meters won't be bundled. And that's a great advantage, because as you see, the first case is where we have the whole thing bundled, is in our experiment. But if you just tie every 4 feet of that same cable and the rest is loose, you get 9 dB of improvement in alien crosstalk. And if you just lay them around themselves without tying them at all, like in a conduit of such form, you get 20 dB improvement. That's equivalent of a Cat6A type cabling. And doing that, we get great improvement. In a case that less than 80 meter is bundled, the rest is open. Even in a 24K cables of Cat6 bundled together, the center cable, as you see, all of it still meets the 5G limit line. And that's a great advantage that means pretty much in all real cases, we can even run 5G as long as the cable is Cat6. At the end, in conclusion, the ever-growing demand for bandwidth, especially in enterprise and in other places, is pushing the network for higher and higher speed in the cabling structures, and especially in existing structures where we've had 1G for over a decade and no really upgrades to it. There has been like this great demand to extend the bandwidth to the next level, and 10G, of course, wasn't possible because the Shannon capacity of these cables didn't really allow it. And back in 2012, we came up with these new technologies for 2.5G and 5G upgrade of the existing network, and we delivered the first chip in 2013 to be able to, and demonstrated the operations over different configurations of these cables. And right now, we are shipping in volume since it's almost over a year that we've been shipping these products in volume, and we believe that this is going to be the next generation of enterprise PHY that will replace the 1G PHYs. Thank you very much. Any questions?
Well, that's great from both Ramins. We have time for a couple of questions before the break. Do we have some people out here who might be wondering about this? Wow.
Everybody believes it.
Everyone, right. Okay, thank you very much again then.